So the first models we will look at are models where the dependent variable is binary, has two categories. You vote yes or no in a referendum. You start a war or do not start a war. You vote yes or no as an MP in Parliament on a law. You candidate yourself in an election or not. You take part in an election or not. Many variables we can think of. In fact, in political science, this is a very, very common kind of variable. Probably more common than skill continuous variables. Now, if you code the binary variable as a 0 and 1, so one category becomes 0, the other category becomes 1, you can sometimes treat it as a skill variable. And in fact, you could run a linear regression and it's not wholly unreasonable. It has problems, but it's also commonly applied. We call this the linear probability model. And you're basically treating the prediction of the linear model as if it's a probability. In economics, this is very common. In political science, this is very difficult to get published. Just different academic traditions. When the dependent variable is reasonably balanced, so you have a similar number as ones and a similar as zeros, then probably the linear model and the more advanced model are going to lead to very similar results. So we're going to look at a lot of criticism of this using this linear model, and we're going to see how we can improve this. But for reasonably balanced data, you're actually going to not find very considerable result differences between those two. Now, what are the problems? The first problem is unreasonable predictions. If you predict a linear model, a linear probability model, you can easily have a combination of x and beta where you predict a probability that is less than 0 or greater than 1. And this does not make much sense. The second problem is that you have induced heteroskedasticity. We assume that the error variance is the same across the line. So whether you have a low predicted y or a high predicted y, the variation of the actual observations around that line should be the same across the line. When you have a linear probability model, you're going to get very different errors that have nothing to do with the normal distribution along this line. Yeah? So if you predict something like 0.5, you're going to have some observations that are exactly 0.5 higher and observations that are exactly 0.5 lower, but nothing in between. If you predict a 0.9, you're going to have some observations that have an error of 0.1 and other observations that have an error of minus 0.9, but nothing in between. So you're going to have very peculiar shape to the residuals that have nothing to do with the normal distribution that we assume when we perform, for example, the t-test. So the testing becomes problematic. And the third problem is that we would really not expect the effect of a change in x to be the same on y regardless of the other variables. If we already predict an outcome to be very, very likely, say we have a 0.9 prediction of an event happening, and x increases a little bit, it can't increase the probability by all that much because we're already at 0.9. There should be a capping effect. So the effect of any change in x on the probability of observing a 1 should really reduce if the prediction is already very high. And the same, of course, towards 0. So, for example, a logistic regression, one of the generalized linear model regressions, addresses all these concerns by having a nonlinear relationship between x and beta and the predicted y. And you can see here this S-curve that shows this nonlinear relationship. And we see that it addresses the tapering off of the effect of x on y when the line gets close to 0 or close to 1. We see that there are no predictions outside this 0 to 1 range. And we address the problem of heteroskedasticity by assuming a different distribution on y. The stochastic part does not have a normal distribution, but a binomial distribution. So the logistic regression is a regression where there's a linear relationship between x and the log of the odds ratio of the dependent variable. So if you calculate the probability of observing a 1 divided by the probability of observing a 0, we have the odds ratio of this binary variable. And we take the log of this odds, and then that quantity has a linear relationship with x. If you move things around a little bit, you will see that that means that we get this equation for the relationship between x and the probability of observing a 1. And in R, this can be very straightforwardly implemented with this command here. And then you can look at the coefficients in a very similar way to how you look at coefficients in a linear model. So here's an example of looking at a survey after the marriage referendum in Ireland, and looking at predicting voting yes. And so we get coefficients that look very similar to the linear regression. They are positive, negative signs. They have standard errors. We can put stars when we see a statistically significant effect, and so forth. The interpretation is similar in the sense that a minus means a negative effect, a plus means a positive effect, 0 means no effect, and the t-test compared to no effect, to 0. So the whole interpretation here is very similar to that for linear regression. Where it changes is that we cannot say this line like where x increases by 1, y increases by the coefficient. We can't say that because it depends on all the other x variables, because it depends on where on the curve you are. You remember that we had an s-curve, and so the slope of this s-curve changes depending on where you are on the x-axis. And so we can't assume this constant effect. And for the stochastic part, we assume a binomial distribution. That is a distribution that only has zeros and ones as an outcome. So we have a systematic part, which is this nonlinear transformation, this S-curve, of the linear relationship between x and betas. And then we apply, that is then our predicted probability, pi on this slide. And then we use this predicted probability to work out the binomial distribution, which is a probability distribution for many events where, for an event where only 0 or 1 can be the outcome. And as we discussed in the class on maximum likelihood, once we know that this is the systematic part and this is the stochastic part, we can work out the likelihood function and the log likelihood function. We can simplify it a little bit. And we have the function that we can optimize with to find the optimal value for beta. So you will see that there's only one parameter here. There's no, the stochastic part does not have its own parameter. There's no equivalent of sigma squared. So we just have to optimize with regards to beta. And that's the only parameter we need to estimate. The variance is fixed. Now one complication is that it's difficult to interpret the size of the effect. Because the impact of x on y changes depending on the current predicted probability, on where you are on this S-curve. It is not a straightforward interpretation. And that hampers a little bit how you publish this, how you interpret this. If you get a minus 0.5 coefficient, is that high or low? We don't know. So here I will outline a few different ways in which you might present results from a logistic regression, or indeed from regressions we discuss later, in different ways to your readers. So one thing you can do is to plot the relationship between x and y, so you can see how it changes. Now one problem is that it always depends on the other values of x and the other betas, because it depends where we are on the S-curve, and that depends on all values of x. So what we can do is, for example, keep all the other values of all the other x variables at their mean, or maybe at their median. Typically I find median a bit more useful. So we might keep all the other variables at their median, calculate the predicted value of y, when we change the one x variable we are interested in from low to high. So because we need all x's every time, all x variables, we just fix all the other variables. We calculate the medians, we set every x equal to its median, and then one of the x's we change from low to a high value, and then we can plot how the predicted value of y changes in those circumstances, given our values for beta. Now we will talk a little bit later about uncertainty. On this example you see a red line, which is the predicted value of y, but you see also these little gray lines. They show how certain we are. They show some uncertainty in our prediction. That is done through simulation or bootstrapping, which is the topic in 2 weeks' time. An alternative way to present results is to look at fitted values for particular changes or particular scores on the variables. Here the relationship is shown between being Republican or Democrat and the amount of donations somebody received. This example is from a vote in a law related to the automobile industry, where they looked at how much financial support, how many donations do these different members of Congress get from the automobile industry, and how do they then vote. So the dependent variable is the vote, and the independent variable is party affiliation and donations. And again, we keep the other variables at medians or means, And then we can calculate predicted values. And again, we have uncertainty as well, here by the 95% confidence interval. And again, that is done through bootstrapping or simulation. Instead of predicted vote for specific scenarios, we can also look at predicted changes in values, changes in probabilities, holding everything else constant. So again, we can put all the other variables at the median, and then we can look at how much the predicted probability changes if we go from Republican to Democrat, or from 10,000 Indonesians to 20,000. And the fourth way is a little bit less relevant for publications, but I would often use it to get a quick read of the regression table in my head by myself. And this is, if you divide the coefficient by 4, you get the slope of the line at the point where the predicted probability is 0.5, exactly halfway this S-curve. So divide by 4 and you have the slope at that midpoint. Now in this particular example, a few slides back, we already saw that there is not even any reasonable value where the predicted value is 0.5. So, sometimes this is a realistic possibility, sometimes it's not. It depends on your x values and the beta values. But it gives you at least some idea how to read those coefficients. So then you can read it in the old-fashioned linear way. If x increases by 1, how much does y increase? But it's only true if the predicted probability at that point is 0.5. And in text also, you can use these kind of calculations to formulate what the impact is of a particular variable on the outcome variable. And if you are familiar with bootstrapping or simulation, you will also be able to provide indicators of uncertainty around this. This is estimation uncertainty, not fundamental uncertainty. So just presenting the regression coefficients will not get you very far because people don't know how to read them. You need to take another step in these kinds of models by coming up with humanly interpretable quantities and that people can understand and interpret, like in this example. There's also an alternative way in which we can look at the same model. So I'm still talking here about logistic regression. So imagine we have a latent variable, a variable that we do not observe. You can think of it as a utility function, the utility that is associated with a 1, with a positive score. So this latent dependent variable we will call y star. And then we might have some probability distribution associated with this continuous latent variable. So this is not a binary variable, but a continuous variable. This continuous distribution function will be a function of the linear relationship between x and beta. And then we just have what we call an observation mechanism. We say that we observe a 1 when y star is greater than 0, and we observe a 0 when y star is less than 0. So we have a continuous variable that we do not observe, that we just imagine there to be, that represents something similar to a utility function that captures an underlying pattern that then is represented by the 1s and 0s we observe. And if this F distribution is a standardized logistic distribution, we basically have the exact same model that we had before with the logistic regression. So this is a different way of thinking about the mathematically same model. So if we have this continuous variable that is a function of x and beta, and that when it's positive we predict a 1 and if it's negative we predict a 0, we might as well assume that it has a normal distribution since it's a continuous variable. So that will bring it more in line with how we think about linear regression. If you think of that distribution f as a standard normal distribution, standard meaning that the standard deviation is 1, so it's fixed, then we have what we call the probit model. So the probit model is quite similar to the logistic regression. Both can be represented with this latent variable y star. Both are related to a linear combination of the x variables. And both have a bell shape curve that is representing this probability distribution, where we can look at the probability of observing a 1 by looking at the probability density that is greater than 0, and the probability of a 0 by looking at the probability that it is less than 0. So in a threshold model we have this bell curve. We look at the point where it is 0, like this dotted line, and the surface under the graph on the right of this dotted line is the probability of observing a 1. The surface under the graph to the left of this dotted line is the probability of observing a 0. And if that curve is the standard logistic distribution, we talk about the logistic regression. And if it's a normal distribution, we talk about probit. So in the probit, The systematic part is the cumulative normal distribution, the cumulative standard normal distribution, that we use as a function to translate this linear relationship between x and betas into a predicted probability. And then we have the same binomial distribution for the stochastic part that we also saw in the logistic regression. The main difference is going to be that the logistic regression has somewhat fatter tails. So the bell curve for logistic regression has fatter tails than the bell curve for a normal distribution. And this means that when the data is very skewed, we have many more ones or many more zeros. Logistic regression could be a little bit better at predicting it because it has more probability weights at the extreme ends.